Hi there, class. This is another video recording. Today we're going to talk about light. As you can see on your screen, well, first off, remember, if you ever have any questions or comments, feel free to email me at any point. I'm very helpful, open, and honest, and I will not ding your grade for any complaint to me. We also have supplemental instruction, as you can see here on the right side of your screen. It's very helpful, and it looks like she's available quite a bit. So, and remember, no food or drink in the lab, and cell phones must not be out in the open. You get a call, just kind of walk to the hallway, and you can take it out there. I know everyone has jobs and kids, so I don't mind when you do go out and check your phone. So today we're going to talk about light and a lot of different parts of light, starting off with the spectrum and ending with LED light bulbs, which I kind of added to the chapter myself, just because I think it's very important. This is the second of two parts. Last week was one part, and we can go from there. Okay. Just some quick terms on light. You have luminous. That means when something produces light, kind of like the sun here. Actually, let me start the presentation. I don't know how to get my picture up there. Oh well, you can hear me. Luminous is when something produces light, like the sun. And incandescent is when visible light is given off as a result of high temperatures, like a light bulb. Electromagnetic spectrum is a complete range of frequencies. So it's everything from a radio wave to a gamma ray at the high end. So just remember that your radio is on the range of frequencies for the electromagnetic spectrum. Whoa. I don't know what happened there. Okay. So, bioluminous is when plants or animals produce light. That could be glowworms, fish, jellyfish, squid. 90% of deep ocean life will produce its own light. Lightning bugs will produce their own light. Now, I think the males will fly around at night producing a pattern, and the females on the ground also produce a pattern. And I think when one of them likes the other, they join up and mate. So it's kind of neat that the lightning bug is actually out there using its mating call, which is a light. We have the electromagnetic spectrum here, which I've listed. You have gamma rays, X-rays, ultraviolet, visible, infrared, microwave, and radio. So it just goes from left to right here. As you go to the left, on this example, you have a shorter wavelength. As you can see here, the waves are closer together. You have a higher frequency, because the waves are more frequent when they have a shorter wavelength. And you also have higher energy. So remember that. Gamma rays have higher energy than radio waves, which radio waves have a longer wavelength, lower frequency, and lower energy. So take a look at that slide there real quick, and as you can see in the middle, you can see the visible light, which ranges from red, orange, yellow, green, blue, and violet. So the visible spectrum makes up a very small part of your electromagnetic spectrum. Okay. So, well, let me fix this slide. Real quick. Sometimes the formatting messes up in between when I okay. So the light ray model. This is the idea that the sun, when it produces light, or something else, when it produces light, it shoots a ray at you. So the light's not in a wave. It's in a ray. It just shoots it straight at you. This model says that light travels in straight line paths. It helps show a couple properties of light, such as in a mirror, the light will bounce straight off. And you have an angle there on the right you see from that mirror. And you also have ordinary objects wherein the light will hit, it'll bounce off in straight lines. And another term to learn is diffuse reflection. It provides light to places like under tables and under trees. So just remember a reflection. Like, how does light get under a tree if the tree is blocking all the light? Well, the sunlight will hit something, reflect off, and it'll diffuse out and provide light underneath that tree. Another formatting error. Okay. So, other terms to learn. Transparent. This is what allows transmission of light through them. Opaque, which means it allows no transmission of light. So if something like something opaque would be like our textbook here. If I would block a light bulb with it, it would block the light. It's opaque. If it's transparent, it would allow the light through it. So what can make something opaque? Well, a mirror can be opaque because it reflects off all the light. Or it can be an absorber. If it absorbs the light, like a black wall. Black paint on a wall. It absorbs light. So, what happens with absorbed light and reflected light? Well, remember, light carries energy. Remember, light carries energy, so it cannot be created or destroyed. So whenever light hits something, you just got to remember that the light just doesn't disappear. It goes somewhere. It has to go somewhere. It does not just get destroyed. Just like with energy. Energy cannot be created nor destroyed under any circumstance. So light cannot either. So remember that light carries energy. And so what gives an object its color? It gives its color by what color that object will put off. So if white light hits green grass, usually all the other colors are absorbed besides green, or two colors that would make green. And it's reflected off that grass, and that's what you see. So what happens to the other light that hits that grass? Some of it is absorbed. Some of it's absorbed in chlorophyll, and that's converted into energy for that grass to grow. So what happens to absorbed light? It gives up its energy to its material and may also show up as a temperature increase. Like on a black wall, if you shine a light on it, it's going to increase its energy. Or temperature, temperature. So reflection. Most objects you see are visible due to diffuse reflection. Consider an object, such as a tree. Each point on the tree must reflect light in all directions, since you can see any part of the tree from any angle. So, light hits that tree and it scatters light in all directions. Because if it didn't scatter light in all directions, you wouldn't be able to see the tree from all angles. Mirrors do not have much diffuse reflection, as other smooth surfaces do not, such as at my desk here. It must not have much diffuse reflection because it is really smooth. I can tell it has a lot of glare, but so. Let's see what slide we're going to now. Slide 11. Make sure I'm not going too fast. I guess you can always pause it if you want to go backwards, although that probably takes a lot of time. I know up at Purdue I used to have trouble paying attention in some classes, so I would just listen to them online. That seemed to help a lot. Because I could pause it and go watch a football game or something, and then come back. Sometimes it'd take me 5 hours to go through a 2-hour lecture. But, so, let's see. We have curved mirrors as our next topic. I mean, we're talking about reflecting light, so let's just talk about curved mirrors for a minute. So... trying to see how I can get the camera up while I'm talking, but whatever. Not that important. Okay, concave with a center part curving inward. This will give an enlarged virtual image. It's one way to have a tricky mirror, is to have an enlarged virtual image. Or it's also used in telescopes to form a real image for you to see. To take something really small and make it bigger. Or you can have convex. That's where the mirror bulges out. This is often used to increase your field of vision, like a side view mirror, where it tells you objects in the mirror are closer than they appear. That's because it's a trick mirror to help improve your field of vision. Let's see. So, this mouse is terrible. Okay. Put the mouse down. When a light ray moves from one transparent material to another, such as from water through air, the ray undergoes a change in the direction of travel at the boundary between the two materials. Basically like sunlight coming through the atmosphere. It's at a certain angle, it's traveling at a certain speed. It hits like the water in a lake. It immediately changes direction. And that's called refraction. So basically, I mean, light's going to travel at the speed of light. But this speed changes from one transparent material to the next, such as from water to air to a vacuum. And when it does this, it changes its angle. That's why, if you remember people who fish with spears, like Tom Hanks in Castaway, the fish is not where you think it is because of the angle of refraction. So if you just, I guess, throw your spear a little bit off, you'll be better. Dispersion and color. So, did everyone get that slide? Refraction. Light is going to change angles as it enters, when it changes from one object to another, from one material to another. So, dispersion and color. So we have a formula. This is the speed of electromagnetic waves, which speed is going to be like meters per second, equals the wavelength. Wavelength it can be in meters, times frequency. Frequency is going to be in hertz. So that's per second. So meters per second on the left equals meters times per second. And I need to come up with some examples. We'll go through those here in a minute. I didn't get them ready before the video started, so it'll be a little slow. Okay. Good old Roy G. Biv. Roy G. Biv. It's going to be really good for you to know the name Roy G. Biv. I used to think there was an I in there between the B and the V. But everything I see nowadays is just R-O-Y, G-B as in boy, V as in Victor. It's the colors of the rainbow in that order. So, as you move left to right, there is a decrease in wavelength. Let me check that with my other slide. Yeah. Everything gets slower as you get towards violet. Violet is going to have lower energy. Violet's going to have higher energy in a shorter wavelength. I'm going to type that in. Violet will have shorter wavelength, higher energy. Red will have longer wavelength, shorter energy. So, that's going to be important for you to know that red will have longer wavelength, lower energy. I'm getting backwards with mine. So red will have longer wavelength, lower energy. And if you go back to my previous slide, you can see that red over here has a longer wavelength and a lower frequency and a lower energy. And I believe that's going to be important for you to know. And also you can just kind of remember red's on the side of radio. Red radio. Remember red radio. And then violet's over here with X-rays and gamma rays. So maybe remember a violet X-ray machine. Make you think that violet's over there. Of course, you got microwave over here too, and infrared. I know they build a lot of radar systems with infrared technology. So remember, Roy G. Biv is the colors of the rainbow. Left to right is a decrease in wavelength. Left to right is also an increase in frequency. So a light wave has a wavelength of 5. This practice problem. A light wave has a wavelength of 5.6 times 10 to the minus 7th meters. What is the frequency of this wave? Let's see. Speed of light is 3.0 times 10 to the 8th meters per second. So that's going to be on the left side of the equation. And that will equal, let's see, well, where am I getting this equation from? Let's see. Right there. Speed of electromagnetic waves, which in this case is going to be the speed of light, equals wavelength times frequency. So wavelength, right there. Let's see, do I have wavelength? Yeah, wavelength of 5.6 times 10 to the minus 7th. 5.6 times 10 to the minus 7th. Meters times, let's see, wavelength times frequency. Oh, frequency. That's what I'm solving for. So I'm going to divide 3.00. Let me get my calculator. And do I have the answer ready? Yeah. So the answer is 5.40 times 10 to the 14th hertz. Which, if I just type it out, it makes me think of Hertz Rent-A-Car. But remember Hertz. Anybody remember what Hertz is? Hertz means per second. So if you don't want to type that, you can say just per second. 5. But it is a unit of frequency. So 5.40, because what I did was I divided the left side by this 5.6, so I just moved that over. Let's see, equals frequency. And that problem is from page 190 in your textbook. So what we did was we solved for frequency there. We have the rainbow here on our next slide. Rainbow. Surface tension. So where's the rainbow come from? This slide's going to teach you where the rainbow comes from. Also have a video down here, but I'm not going to show a video in a video because this video will take forever. So I'm going to post the video to Blackboard. It's 9:44 at night, so you will probably be getting some notifications on your phone if you're like me. I'll post something to Blackboard, then a half an hour later I'm trying to sleep, and it'll inform me that, yeah. But, yeah. So, between that and Amber Alerts for something that's 6 hours away, which is kind of weird. I got 3 of those today, all over town I did, but whatever. So, the rainbow. Surface tension pulls raindrops into a spherical shape as they fall through the air. And it turns them into a raindrop. But it turns it into a special type of drop, special shape. Sunlight strikes it. So let's imagine sunlight striking this single spherical raindrop near the top of the drop. So it's coming in on top. So the light's refracted a little bit, but and then it's reflected on the other side of the raindrop. So the raindrop, the light does not want to leave the raindrop. So it's reflected. And when it's reflected, it's refracted again on its exit. In this refraction, it's a refraction, reflection, and then a refraction, which is going to be important for your quiz or test. This combination produces a rainbow. It separates the light colors into Roy G. Biv. Red, orange, yellow, green, blue, violet. And here's a video, really good video for you to watch, which I'll post to Blackboard here in a little bit. So we had a big controversy here about 300-400 years ago. Newton kind of started it. He said that's Isaac Newton, said that light, if it were a wave, it should bend as it moves. It should bend like waves in a pond. So Newton was kind of for the particle theory. And he kind of came out with some experiments on this side of the particle theory. There's evidence of the wave theory. Thomas Young in 1801 produced 2 light waves, one in crest while other in trough. Light waves fall on a card with 2 slits, each less than a millimeter in width. So, man, I wish you almost have to watch the video. The video is amazing, and it's really hard. Pretty soon, I'm gonna get something that I can draw on, like a tablet, which I have a tablet, an iPad. I don't know how to hook it up to this thing though. I'll have to figure that out. But the video is going to show it. So you pretty much have two waves produced. And as the waves go out, since they're produced from different spots, the waves will collide. At one point they collide with one in crest and one in trough. And then they'll collide at other points in their waves too. So that sometimes the light will be bright, sometimes it'll be dark. It'll be bright, dark, bright, dark. It's really neat. And the video I have is just amazing. So light is produced and is shown on this index card with 2 slits. Very tiny slits. And then waves are produced from these slits in an arc. So a series of bright lines on a screen behind the card is produced. This phenomenon is called interference. So in the center, on this light they're shining on, it will produce a very bright light. And this is called constructive interference because they construct together. And then above and below line, light arrives at different time. When one light beam arrives half a wavelength different than the other beam, this is called destructive interference because one arrives in crest and one in trough. So they cancel out. And here's the YouTube video right here. That's amazing. Okay. We also have something called polarization of light. like polarized sunglasses, like if you want to look really cool. You've probably seen them advertised. Polarized sunglasses, which I think some at your local Walmart are $4, and then you go into the Vision Center and they're $40. So I don't know the difference. I'm sure that the $40 ones work better, but plain polar. So when light vibrates, it vibrates in all directions. So if you think of light going up and down as it comes at you, it's also going this way, this way, this way. So it's like it's vibrating every which way. And then almost you think of it as a plane. It's coming at like a plane. It's vibrating that way, that way, that way, that way, that way, that way. Plane polarized refers to light only vibrating in one plane. So the polarized sunglasses are going to block out all light except that one in that one plane, so that you can still see everything. But it's going to help reduce glare, because it's going to block out some of that glare coming from objects that are in a different plane. So to tell if something's polarized, you just rotate one pair over another pair, and it'll block. When they're at a 90-degree angle, it's blocking. The first pair will block all sunlight except in that one plane. And then the second pair will block what's in that other plane. No light will get through. So there's several ways to produce polarized light. You can have selective absorption. Light in one plane is transmitted through a crystal. So the light will transmit one plane through it. All the other light's absorbed. This is what Polaroid uses to produce their pictures. And this is what made them a lot of money, was that they use this type of technology. So that's selective absorption. So you selectively absorb most of the planes and you allow one through. You also have reflected light. This is the reasoning behind polarized sunglasses. Some light that's reflected is reflected in a certain plane. So your polarized sunglasses will block this plane, and you don't see that glare. You also have scattering. Light is absorbed and re-radiated by particles in the air. This is the reason behind why the sunset is red and orange. Because in the daytime, the blue light gets through and makes your sky blue. But at sunset, all the blue light is absorbed and re-radiated by particles in the air, because the sunlight has a lot more atmosphere to travel through. And all the blue and violet is scattered before it reaches you. So so scattering is the reason your sunset is orange. Now we're going to go through some technology. Fiber optics. Fiber optics. The communication capacities of fiber optics are enormous. A single fiber, the size of a human hair, can carry all the internet transmissions and all radio and TV broadcasts in the USA at one time without interference. Isn't that amazing? Just think about that for a second. A single fiber, the size of a human hair, can carry all internet transmissions and all radio and TV broadcasts in the USA at one time without interference. Due to this fact, that light has tremendous range of frequencies. That's why it's possible. Fiber optics are used for the internet, some telephone calls, Christmas trees, store displays, and used to guide and perform some surgeries. And here I have a little video at the bottom if you want to view that. I'm going to post that to Blackboard 2 in a minute. Fiber optics. Light can reflect down a fiber for 50 kilometers before needing to be amplified. That's because the light in the fiber optic strand will reflect back and forth, eventually just going straight down the fiber optic line. Uses total internal reflection. Usually pure silica glass is used in the middle. That's just a fact that you might want to know. So those were all kind of, before was all some stuff that, like the polarized light and the interference pattern, was all stuff that kind of proved the point of waves. But then they came out with a couple things that kind of said that light was a ray or a light beam. For instance, the photoelectric effect used in solar cells. The movement of electrons as a result of energy acquired from light. Some of the experiments they used on this kind of proved that. So light is considered to be dual nature. Acts as a wave and as a particle, which is really hard for a lot of people to understand, and it's hard to think about. Experiments today can prove light to be one or the other, but never in one experiment is light both, and that's amazing. So light is considered to be a wave and a particle, but never both in the same experiment. So now just to talk about the theory of relativity real quick. If you can remember who came out with this, Albert Einstein. So if you are chasing a beam of light and you're right on it, traveling with it, are you also moving at the speed of light? That's just a theoretical question that I think Mr. Einstein asked. My startup disk is almost full. So at the age of 26, Einstein published an analysis of how space and time are affected by motion. Let me do something to my startup disk. Yep, ESPN. My startup disk is almost full. There we go. Ah. There's. What is this screen? My old screen. Well, maybe I am being videotaped the whole time. Let's see. Okay, back to the theory of relativity. So this is kind of saying that everything is relative. So, I mean, right now I would look at myself and say, I'm not moving, I'm at rest. Well, the Earth is spinning, I don't know how fast. I just came up with this idea, but let's say it's spinning 1,000 miles per hour. So if you're out there in space and you're seeing me spin, am I moving 1,000 miles per hour? Am I? So at the age of 26, Einstein published an analysis of how space and time are affected by motion between an observer and what is being measured. 11 years later, he came up with an interpretation of gravity as distortion of space and time. So gravity is distorted by space and time. I'll give you an example here in a second. I'll give you an example right now. Example of observing objects at different points of view. You are traveling on a bus at 100 kilometers an hour down a highway. An insect flies from the back of the bus at 5 kilometers an hour. So while you're on that bus, that fly is dropping at 5 kilometers an hour. Versus the bus, the insect is flying 5 kilometers an hour. To someone on the side of the road, this insect is flying at 100 kilometers an hour, plus or minus 5 kilometers an hour, because that's how fast the fly is traveling, depending on if it's going forwards, backwards, or sideways. All motion is relative to a reference. Very important line right there. All motion is relative to a reference. Just very important. So, Einstein's special theory is based on two